Hello, this is Mr. Gumler with the 7.4, the triangle proportionality theorem and its converse. So today we're going to prove this triangle proportionality theorem, or to us the TPT, and we'll also find that the conditional of that has a true converse to it, and we'll also prove that converse today. Before we get into what the triangle proportionality theorem states, we do need to start off with a pair of lemmas. So recall what a lemma is. A lemma is a helper theorem. It's a kind of a pre-theorem that is going to lead us into a theorem of more significance. And so I want to introduce to you two theorems here. We have the lemma proportion entailment A and the lemma proportion entailment B. Let me unpack both of these for us real quick before we move on. So in the first statement, as we see, look in proportion entailment A, it says if A over B is equal to C over D. Essentially, it's saying if we have a true proportion. So if we know that this proportion A over B is equal to C over D is true, then we're allowed to actually manipulate the proportion in different ways. And this manipulation in particular is we're taking the numerator value on each side of our equation and adding it to the denominator value of each side of our equation. So notice that I'm transforming the proportion. I'm taking A, the numerator value, and adding it to its denominator B. So I have now the proportion A ratio to B plus A. I'm doing the same thing on the right-hand side as well, taking C and adding it to its denominator D. So I have the ratio now of C to D plus C. Now it does change the ratio value. However, the proportion still remains true. And we're actually going to see the use of this proportion entailment A in our proofs today. And then what follows that is this entailment B, which again starts off the same way. If we have a true proportion, A over B is equal to C over D, then another way we can manipulate our proportion is take our numerator value and subtract it from our denominator value. In other words, we can say A over B minus A is equal to C over D minus C. Now, with any lemma, right, these are still theorems, we do need to prove these two are true, which means on the worksheet, you'll find that I have proven the entailment A for you already. What you'll do is use that example then to help you prove the entailment B, all right? So I've shown A and you're going to do B, but both of these are going to be important for us as we dive into the proofs of our triangle proportionality theorem and its converse. So let me introduce you to the triangle proportionality theorem, or to us, the TPT. So it's what it says. If a line through the interior of a triangle is parallel to a side, then it cuts the other two sides proportionally. Now let's bring that conditional to life in a diagram. If you take a look at our diagram below, we have triangle ABC, such that this segment DE is cutting through our triangle parallel to the third side. So DE is parallel to side AC. That's what's given. As it turns out, what point D and point E do is they divide our sides AB and BC up into two parts each, which means we've got four quantities there. And as it turns out, those four quantities are proportional to each other. As we see, our proof statement is that BD ratio to AD is going to be equal to BE to EC. And that's what we're going to prove. So knowing that DE cuts through our triangle parallel to that side AC, let's arrive to our conclusion that this proportion of these four parts, these four segments, are actually proportional to each other. So where we begin in our proof is with similarity. Right off the bat, if we take a look at our given triangles here, ABC and DBE, knowing that DE is parallel to AC, right off the bat we have these two triangles similar. Hopefully you notice that what we're dealing with now, if we have parallels, we have transversals. And what transversals do as they cut parallels is they give us some angle relationships. And in fact, we know that there's several angle relationships going on in this case, but one in particular is to note that we do have these corresponding angles. So notice right off the bat that angle A is actually equal to the measure of angle BDE. And at the same time, we can find that these two angles here, angle C, is equal to the measure of angle BED, and that gives us now two angles of one triangle are equal to two angles of another. So we can call the two triangles similar, right? We have these two angles. We can call these similar. Why? Because of angle-angle similarity. So immediately we've got similarity between the two triangles. But with similarity, we can then untap its potential. Remember, the second part of the definition of similarity is not only know the corresponding angles are equal, but the corresponding sides are proportional. So in particular, there is a pair of corresponding sides that I'm going to pick out from these two triangles and form a specific proportion that we're going to carry with us onto the next slide. So the proportion I'm looking at is this. I'm going to take BD, which is the side of our smaller triangle, and ratio it then with its corresponding side, AB, right? We know the two triangles are similar, and that means BD and is corresponding to AB. What I can do with that is I can then set up the proportion of a second pair of corresponding sides. I'm going to choose BE, which is, again, the smaller side of my first triangle, ratio it with its corresponding side, BC. And I grab this right from the heart of similarity. So because the two triangles are similar, and by the definition of similarity, we have this proportion that we're going to take with us to the next slide. So now we have this new proportion we know to be true, that BD over AB is equal to BE over BC. What can we do with that then to arrive to our conclusion? This is where the lemmas step in. In particular, I'm going to be using lemma, the lemma proportion entailment B. Let me remind you what the lemma proportion entailment B stated. It said that if we have a proportion that is true, then what we are allowed to do is take the numerator value and subtract it from the denominator value. In other words, we have this proportion that we just proved to be true. BD over AB is equal to BE over BC. Let's take our numerator values and subtract them from our denominators. So the numerator value of this newly manipulated proportion, it doesn't change, right? I'm just taking the numerator value and I'm subtracting it from the denominator. That's what changes according to our lemma. I'm subtracting BD from the denominator. Do the exact same thing on the right-hand side of our proportion. BE, right, stays the same, the numerator, but I'm taking BC and I'm subtracting BE away from it. Now think about what's going on in that denominator of this newly formed proportion. I'm taking this entire side length AB and removing this length BD. Same thing on the right-hand side. I'm taking this entire length of BC and removing that length of BE. What remains then if I took the whole segment and removed its part? Well, what remains is the other part, what the other parts of our entire segment. So using our whole minus part, I can then conclude that AB minus BD simplifies to just simply AD. And the denominator of my second ratio there, BC minus BE, just simplifies down simply to be EC. And we have arrived to the conclusion that we were looking for, that the four parts of these two sides of a triangle, BD, AD, BE, and EC, are proportional to each other. So this is our conclusion to our proof of the TPT, so QED. Okay, we've arrived to the end. So really, the proof is not tricky. It did require a little bit of guidance showing you where to start, right? Well, we start with the first part of just finding similarity. So with the necessary information, we prove the triangles to be similar. And then from definition of similarity, grabbing our proportion and applying our lemma PEB, we arrive to this conclusion that yes, if we were to cut through a triangle such that that cut line is parallel to a side, then it cuts the remaining two sides proportionally, cuts it into four proportional parts. Now, the TPT has a converse. So the converse TPT, what does this state then? Well, think about what we do with the converse. We exchange our given and conclusion. So our converse states this. If a line through the interior of a triangle cuts a pair of sides proportionally, then it is parallel to the third side. So in other words, we have this segment DE, in which we already know it's cutting the two sides of our triangle into proportional parts. What we're going to conclude is that that segment DE is in fact parallel to AC. So in this case, notice that our given, our diagram is almost identical to our original conditional. The only thing we don't know at this point is that DE, right, is not parallel, or is not given to us as parallel as AC. But we do have the given proportion that BD to AD is equal to BE to EC. I'm also going to walk you through a proof of this one in our slide notes here. So let's take a look at where we start with the converse of TPT. With the converse, we actually start with applying one of our lemmas. In this case, we apply lemma A. What lemma A does, let me remind you, is we are allowed to take the numerator value of a proportion and add it to its respective denominator value. So we're given already, right, just from the given of this proof, that BD over AD is equal to BE over EC, which means we already have an established true proportion. Let's apply lemma A. So take our numerators and add them to their respective denominators. So I have BD, doesn't change, right? It's still a numerator. Let's add that to our denominator, AD. So AD plus BD. I can do the same thing on the other side of our equation. BE, I'm going to add it to its respective denominator. So think about what we're doing there, right? I'm taking BD and adding to AD. I'm taking BE and adding to EC. What's happening there? I'm adding parts together. So in this case, I can just simply use segment addition postulate. BD plus AD, we can simplify that. BD, right? AD plus BD just simplifies to the entire segment AB. So my ratio on the left-hand side is now BD to AB. And the ratio on the right-hand side can simplify. The numerator stays the same, but by denominator I can re-express EC plus BE. That's really the entire segment BC. So what does this do for us? So we've got this proportion here. Now we know this proportion to be true, right? We just proved it with what we've given and applying our lemma proportion entailment A. Well, we're going to carry this proportion with us now to the next slide because there's something going on here. Let me unpack it real quick. Let me kind of unpack this before we dive into the next slide. What is BD and AB? Well, those are sides of the two triangles, the smaller triangle BDE and the larger triangle ABC, which means those sides ratio together are in fact proportional to another pair of sides of, again, the smaller triangle, larger triangle. What we have here is two sides of one triangle are proportional to the two sides of another. So what comes right after this? Similarity. Now that we have BD to AB and BE to BC is a true proportion, that we have two sides of one triangle are proportional to two sides of another, we can prove these two triangles, or what we conclude about these two triangles is that they have to be similar to each other. Right off the bat, once we have that proportion and we have our reflexive angle there, angle B, I can declare these two triangles, ABC and DBE, similar to each other. So triangle ABC is now similar to triangle DBE, and the result of why that's true is because of side angle side similarity. So we have this, okay? We have similarity between our two triangles thanks to side angle side similarity. Well, why is similarity important here? Well, because it gives us a lot more information. We know that the third pair of sides are obviously going to be proportional to the other pairs, and we know all the corresponding angles are in fact equal. So which angles correspond? We can find that the measure of angle A and the measure of angle BDE are in fact equal, and not only are they corresponding in respective to their triangles, but they are a pair of corresponding angles in terms of transversals. Think about what AB is doing. It's cutting through the two lines AC and DE, which means those are equal corresponding angles. And because those angles are equal and corresponding, we can use our parallel tests way back from our previous chapter in semester 1. We can declare that DE is in fact parallel to AC. So DE is parallel to AC, and this is because of our corresponding angles test, that we have a pair of corresponding angles defined by our transversal, and that means we can show that DE must then be parallel to AC. And so that's a really neat proof, again, showing that the converse of our triangle proportionality theorem is also true. Now, to end our lesson here, I just want to show you this pretty corollary. Now, I am going to leave most of this up to you to figure out on your own on the worksheet, but I do want to kind of nudge you in the right direction. This pretty corollary, so remember recall what a corollary is. It's an immediate consequence of a theorem of significance. So this corollary is actually a corollary of our triangle proportionality theorem. Notice that in the TPT, we had this parallel cutting through our triangle. Well, in this corollary here, we actually have a set of three parallels, and actually this theorem here, this pretty corollary, works with three or more parallels. So what's going to happen here is in our diagram, if we're given that we have a set of three or more parallels such that they're cut by two distinct transversals, then those parallels cut the transversals proportionally. In other words, we can prove that the ratio of AB to BC is the same ratio of XY to YZ. And now how are we going to prove this? Again, it's a corollary. So you are going to what you're going to need to use is the TPT. And in order to use the TPT, that means we have to be forming some triangles. So here's your hint, okay, for this theorem. Simply take point A and point Z and connect them. So connecting point A to point Z, we form this third transversal, right, AZ, cutting through. And you'll note that also we can then say that AZ will intersect that parallel in the middle, BY, and we are going to call that intersection point here point M. That's what I like to call it. So now, with the construction of AZ, you've got yourself some triangles, plural. Notice you have triangle ACZ. Let me draw that one out, ACZ. And you have triangle AXZ. So now thinking about in terms of our triangle proportionality theorem, we have a parallel cutting through actually a pair of triangles. Use that information then to arrive to your conclusion. It's not actually a very difficult theorem to prove because it is a corollary. You already have TPT, theorem of significance, to help you prove this. Again, I'm going to leave that one for you to figure out on your own on the worksheet. So please be sure to hop over to the worksheet and have a look there. Be working on that. If you do come across any questions you need help on, email me. I will get back to you. With that, be good and do good.